Hello everyone, this is Dr. Fan. Today let's discuss a very interesting question about rotation. Even though some college professors cannot solve this question completely, with the knowledge learned in high school, we should be able to predict which system goes down faster. Alright, let's look at the question in detail. Let's see, on the left, we have a ball of mass m and it is connected to a massless rod with a length of L. And on the right, we only have a rod. There is no ball. But this rod has the same mass m and the same length as the system on the left. So the question asks, if released from horizontal, which one reaches the bottom first? So clearly this question is about rotation. And if released from horizontal, if the ball or the rod goes to the bottom here, the angle it rotates is the same. So the angular displacement is the same, which is 90 degrees. So theta is the same. If we know the angular acceleration, we should be able to predict the time. So if you have a larger angular acceleration, then the time would be shorter. So following this, an equation naturally comes to our mind. That is, torque equals to inertia times angular acceleration. So if we are able to find out the torque and inertia, we should be able to find out the angular acceleration. All right, let's look at the left system first. Let's say the ball and the rod rotate an angle of phi, and the ball is right here. So what's the torque at this moment? We know the torque equals to Rf sine theta. R is very straightforward, which is the length of the rod, and the force is also very straightforward, which is mg. So the key thing here is the angle. So this is the angle between the rod and gravity. So this is theta. So if we extend the direction of gravity, then we know this is 90 degrees. So if this is theta too. Then basically we have theta plus phi equals to 90 degrees. So then sine theta is basically sine 90 minus phi. So this equation basically becomes mgl times cosine phi. So we find out our torque. So how about the inertia? The inertia is very straightforward because the rod is massless. The inertia only comes from the ball, which is ml squared. So the angular acceleration for the left system is torque divided by the inertia, which is mgl cosine phi divided by ml squared. Then we have g cosine phi divided by L. That's the acceleration for the left system. Then how about the right system? We can just do the same thing. Let's see the rod rotates an angle of phi. Then we will try to find the angular acceleration from the torque and inertia. So if we look at the torque is Rf sine theta. But in this case, R is different. Why? Because the force is coming from gravity, and gravity is applied at the midpoint of the rod. So R basically equals to half L, and the force doesn't change, which is mg. Then we can do the same thing. This is the angle between the rod and the gravity. We can extend this line. Then we say theta plus phi equals to 90 degrees. So sine theta is basically cosine phi. All right, now let's look at the inertia. The inertia for a rod pivoted at one side is ml squared divided by 3. So then the angular acceleration for the right system is the torque divided by the inertia, which is half mgl cosine phi divided by ml squared divided by 3. If we simplify this, we should get 3g cosine phi divided by 2L. So what did we find out? We basically find out under the same angle phi, the angular acceleration for the left system is g cosine phi divided by L. But for the right system, its angular acceleration is 3g cosine phi divided by 2L. So under the same angle phi, the angular acceleration on the right is larger than the angular acceleration on the left. So that means the right system have a larger angular acceleration, so it will take shorter time for the right system to reach the bottom. So the correct answer is the right system will come down faster. So we used this classical equation solved this question. Let's look at the different method. So let's look at the same question, but thinking about using a different method. Let's imagine our ball and rod rotates an angle of phi. And for the right system, it's the same. Let's imagine the rod rotates an angle of phi. Now let's think about this. For the ball, rod, and Earth system, the only external force is coming from the pivot, but the pivot is not moving. So that means there is no net work on the ball rod Earth system. So its mechanical energy is conserved. Then the initial mechanical energy should equals to the final mechanical energy. If we consider this is our reference height, then the initial mechanical energy is zero kinetic energy and zero gravitational potential energy. But if the rod and the ball goes to this position, then it will move. So it will have a kinetic energy of half I omega squared. And it also have gravitational potential energy, but it is smaller than zero because it's lower than our reference height. So how low? That is the height difference. So if this is L, then this length right here should be L times sine phi. So the gravitational potential energy should be minus mj times L times sine phi. Then this equation can be written as mgl sine phi equals to half I omega squared. And we know the inertia is ml squared. So the equation becomes this, mgl sine phi on the left, half ml squared omega squared on the right. So mass and mass cancels out. There's a length here, there's a length square here. So we should get our omega equals to 2j sine phi divided by L, then there's a square root. So this is the angular velocity of the rod and the ball system at an angle of phi. Similarly, we should be able to find out the angular velocity for the right system. For the right system, it's similar to the left system. Its mechanical energy is conserved. So the initial mechanical energy equals the final mechanical energy. If we consider this is our reference height, we would get a very similar equation. So the initial mechanical energy is zero, and at an angle of phi, its kinetic energy is half I omega squared, and its gravitational potential energy, we know UG equals to mgh, right? But there is one thing here. Remember, the center of mass for the rod is here. So the height it actually decreases is from the center of mass here to the center of mass here. So then this h right here is actually half L times sine phi. So the gravitational potential energy is minus mg half L times sine phi. This equation can be written as half I omega squared equals to half mg L sine phi. We know for this rod, its inertia is ml squared divided by 3. So this equation can be written as half times I ml squared divided by 3 times omega squared equals to half mgl sine phi. So half and half cancels out, m and m cancels out, and 1l has been canceled out. So we should get the omega equals to 3g sine phi divided by L, then there's a square root. So now we get the angular velocity of the left system and the right system. We use a totally different method. We use the energy method instead of the method we used in the previous slides, which is this one. In the previous slides, we found out angular acceleration, but in this slide, we find out the angular velocity. And it's very clear that at the same angle phi, the angular velocity for the right system is larger than the angular velocity of the left system. So the right system will definitely reach the bottom first. You see, we use the knowledge in high school and we predict which one goes down faster. But why did I say that even some college professors cannot solve this question completely? Because it's very, very hard to find out the time from horizontal to the bottom. Why? Because it will involve some pretty complicated calculus. We know angular velocity equals to d theta over dt. So if we use the right system as an example, then this angular velocity equals to root of 3g sine theta divided by L. If we want to find out time, we can write as 1 over 3g sine theta divided by L times d theta equals to dt. We can find out the time from this equation if we take the integration on both sides. But the problem is this is a very complicated integration. This is actually one type of integration called elliptic integration. There is no analytical solution for the time. So that's why I said many college professors cannot solve this question completely. All right. So for today's discussion, we discussed the two very interesting systems, and we used two methods to solve this question. The first method is angular acceleration, basically Newton's second law in rotation, and the second method we use energy. Hope you like our discussion. I will see you next time. Thank you.